This is about the law of sines, which really is one of the most beautiful things in all of trigonometry. Firstly, keep in mind that it applies to all triangles, not just right triangles. The vocabulary used is an oblique triangle, which is a triangle that is not necessarily a right triangle. Here are two types of oblique triangles. One is called acute case, where all the angles are less than 90. The other case is called the obtuse triangle, where one angle is greater than 90 degrees. Notice how right triangle is the transition, the intermediate stage between acute and obtuse. Up here is how we label a triangle. We label the angles with capital letters A, B, C, and then we label the side lengths with lowercase letters, little a, little b, little c. Notice how little b is opposite big B and little a is opposite big A, etc. So the labeling is very, very symmetric. Now here's the law of sines stated down here. Sine of big A over little a equals sine of big B over little b equals sine of big C over little c. See, once you see that once or twice, it's just kind of impossible to forget. It's just so symmetrical between the variables, side lengths and angle lengths. The law of sines actually has a very nice symmetrical generalization to the case when the triangle is on the surface of a sphere, like on the surface of the Earth. The law of sines in the spherical case was actually discovered in about the 10th century AD by sailors and astronomers. The law of sines also played a central role in the discovery of what is called non-Euclidean geometry, which is one of the intellectual high points of the 19th century. Over on the next page, the author restates the law of sines as three equalities. It's the same as stringing them all together. And he also points out how it's used in conjunction with the fact that the sum of the angles, a plus b plus c, in a triangle is equal to 180 degrees. This is what has to change in non-Euclidean geometry, where the sum of the angles is no longer 180 degrees. On a sphere, the sum of the angles in the spherical triangle is greater than 180 degrees. And in something called hyperbolic geometry, the sum of the angles in a triangle is less than 180 degrees. Nevertheless, in those two cases, there are very nice symmetrical variants of the law of sines for those non-Euclidean geometries. Now back to the previous page, there are four cases of an oblique triangle. Let's look at the angle side angles, so we know this angle, we know this side between those two angles, and this other angle. Now, of course, because the three angles have to add up to 180, we actually know the third angle. Okay, so we know one of the angles, right? Here it is. We don't know how far the other vertices are on these two sides, but we know one of the angles. Next, we know this side length. Okay, so we really do know how far along one of these rays to go. So here's that side length. We'll cut it off there, and that's where another vertex is located. Next, we know the other angle, the second angle here. So that means that we know, what this angle is going to be, this angle right here. You can see now that these two rays are going to meet somewhere, and where those meet, that determines the third vertex, and therefore once that's locked in, we know the other two side lengths. Now let's see how to do this with the law of sines. So I've got my triangle labeled in the standard way, vertices with capital letters, A, B, C, sides opposite with little letters. Because we're assuming angle side angle, I mark this angle as known. I know this side as known, and I mark this angle as known. Because the angles have to add up to 180 degrees, and I know these two angles, I actually know this angle up here. So there we go. Now let's look at the law of sines over here. I know sine of C, I know little c, and I also know sine of big A. Therefore, with this first and third one, I can figure out little a. Okay, little a figured out. Now we can look here. We know big A, little a. We know um, big B, so we know this thing here. So that means in this little equation, the only unknown is little b. So therefore, we can use this equation to solve little b. So therefore, we've solved this triangle, the angle side angle case. As indicated here, cases 3 and 4, these two up here, have to wait until the next section when we look at the law of cosines. But the other case where the law of sines applies is in case 2. This is certainly the most interesting case mathematically, and so I'm going to do a separate video about that.